Today, we will be discussing the time complexity of Kruskals algorithm to find the minimum cost spanning tree. If you do not have an idea of the Kruskals algorithm, please watch part 1 for a step-by-step explanation using an example and part 2 for a detailed explanation of the algorithm. Line 1 is an assignment statement and hence the time complexity of this line will be O of 1. The for loop in line number 2 examines the vertices of the graph and hence the number of times this for loop runs will be v, where v is the number of vertices in the graph. Let's talk about the makeset function in line number 3 later. Line number 4 sorts the edges of the graph in non-decreasing order of their weights w, and the best known time complexity of a sorting algorithm is O of n log n, where n is the number of elements to be sorted. In this case, we are sorting the number of edges e, and hence the time complexity of line number 4 will be O of e log e. Line number 5 is a for loop which examines the edges of the graph one by one, and hence this for loop runs e number of times, where e is the number of edges in the graph. Now let's move to line number 9, which is a return statement and hence the time complexity O of 1. Now let's examine the couple of statements which we have skipped. Line number 3, 6, 7 and 8 are the lines which we haven't examined yet. In these lines we make use of functions makeset, findset and union function, all of which are disjoint set operations. The time complexity of these three functions is O of log v. Now let's consider the first chord segment. The for loop here runs v times and hence the makeset function is executed v times. Now let's consider the second chord segment. The for loop here runs e times and hence the findset and union functions are called e times. So if you try to combine the time complexities of the makeset, findset and union functions, you will get a total of O of v plus e into log v. We also know that in a connected graph, the number of edges will always be greater than or equal to the number of vertices minus 1. And hence, we can say that the time taken by the disjoint set operations is equal to O of e log v. And finally, adding up the time complexities of the various chord segments, we get the total time complexity is equal to O of 1 plus O of e log e plus O of e log v. But as we have already discussed, the value of e is greater than or equal to v minus 1. The largest component here in this equation is e log e, hence we can say that the total time complexity is equal to O of e log e. Now we also have a relation e less than v square. This relation is obtained from the fact that the maximum number of edges possible with v vertices is v into v minus 1 by 2. Now let's apply log on both sides of this equation. Thus we can say that log e is equal to O of log v. Using this relation, we may restate the time complexity of Kruskals algorithm as O of e log v. Hence, we can conclude that the time complexity is equal to O of e log e or O of e log v.